Start now to discuss the operations we use usually in vectors. One of the most basic operations, the operation of addition. So why do we need to know about vector addition? Very often you can have a situation where there is a charge at one point in the space. So I will call this charge here Q1, and another charge in another point in space. I will call this one Q2. Each one of them will give rise to its own electric field at another point in space. So I will call this electric field here E1, and I will call the electric field resulting from the second one here. Sorry, my handwriting is not very good. I will call this one here. I will call this electric field here, say E2, okay? So what is the total field at this point here? This is the observation point B. The total field, you have two fields, one coming from the first charge, the other one is resulting from the second charge. The total field will be the vector sum of these two vectors, because each one of them will have its own strength, will have its own magnitude. Then the resultant field at this point is really the sum of both, the vector sum of both. So how do we sum vectors? There are two ways of looking at it. The first one is considered in the diagram in the left. You have a vector A and a vector B. In order to sum them, what you do, you draw, as shown in the right, you draw the vector B from the end of vector A, and the vector C will be the vector closing the parallelogram, closing this, closing the third edge of this triangle here. And mathematically speaking, this equivalent to saying that the vector C, as shown here, is the sum of the two vectors. So you sum the corresponding components, the ax plus bx component from both vectors, ay plus by, this will be in the y direction, az and bz in the z direction. So the vector C will have now three components, x, y, and z, and each one of these components is the sum of the two corresponding components from the two vectors. We say that vector summation is commutative, it is associative, and it is distributive. What do you mean by commutative? Commutative means that if you sum a vector A plus a vector B, and here I bought a bar underneath to indicate a vector, this equal to B plus A. So it doesn't matter, the order doesn't matter. Associative means it doesn't matter what is the order of the operation. So for example, if you are summing three vectors, A plus B plus C, you first sum B plus C and then you add them to A. This is exactly equivalent if you sum A plus B first and then you add them to C. This is called associative operation. Distributive means that when you are doing an operation of a vector, scalars can be distributed. For example, if you are multiplying, say, 5 by A plus B, if you're doing something like that, two vectors A and B, and you multiply their summation by 5, this is equivalent to 5A plus 5B. This is called, say that the operation is distributive relative to scalars. And this terminology, commutative, associative, and distributive, is really coming from vector algebra. So it's coming from linear algebra. Linear algebra is a big science. It's a branch of mathematics, and it discusses all these properties for different types of quantities. One other operation that we have to consider for vectors is the vector subtraction. So if we want to subtract a vector A minus a vector B, as shown here in the left, this is equivalent to adding A to minus B. And the vector minus B, as shown here, is simply another vector. It has the same magnitude as B, but it is pointing in the opposite direction. So this is really, it's a reflection of the vector B. It has the same magnitude exactly, but it's opposite. So if we apply the same operation of summation of A and minus B, we draw minus B from the end of A, and then the vector D will be the vector that closes a triangle. This here will be the case that we have in this one. So this is, so if we take a look at that, so this how it is obtained pictorially, and mathematically this equivalent as shown here in this equation to subtracting the corresponding components, and the order here does matter. So if you say d is equal to a minus b, so the x component of the vector d is equal to ax minus bx, the y component of d is equal to ay minus by, and this component of d is equal to az minus bz. And of course, this, if you move b to the other side, this implies that a is equal to d plus b. This implies that a is equal to d plus b. And why do we need to talk about vector subtraction? It's very common that you have a charge at one point here, q, and you want to calculate the field at another point. And if you will know very soon in this course that the field will depend on the distance, so you have to calculate the distance from one point to another. So so if I call this vector here, I'll call this vector here, which is pointing from the origin to the location of the charge q, I'll call it here rq. And if I call the vector pointing from the origin, and here my drawing is a little bit coarse, but I hope you are getting my point. If I draw, this is a position vector for observation point B, and I want to calculate the distance from Q to B, then I need to subtract these two vectors in order to determine the vector pointing this direction. So I have to get the vector here, which is called RQP. RQB is the vector pointing from the point from the point of the charge Q to the point where we are calculating the field B. And this RQB, as you see from this figure, is really equal to RP minus RQ. So this is why we need to do this subtraction. And of course, if you want to calculate the distance, it's going to be the modulus of the vector RQB. So vector subtraction is used very often in electromagnetics because we need to determine vectors pointing from the location of the charges to the location of the point where we are measuring or calculating the field. And we need very often to determine the distance from the location of the charge or the point of the charge to the observation point. One very important thing that we'll use also in this course is the concept of a position vector. When we say here, as shown in this figure, that the point B has three coordinates, or has coordinates of 3, 4, and 5. So 3 in the x direction, 4 in the y direction, 5 in the z direction. This simply means that its distance from the xy plane is 5, which is equal to 5. And if you project this point here to the xy plane, you get its projection point here, which is shown. And this point, as you can see, will have coordinates of 3 in the x direction and 4 in the y direction. Now, the position vector is a vector pointing from the origin to the point. And it is not only a vector, but it is a line as well. It defines a line because there is a point of reference, and this point of reference is the origin. Okay, so this is very important to understand this. Position vector defines a line because it has a reference point. It must start from the origin. And it is pointing in the direction of the point of interest here. So in general, if a point has coordinates of x, y, and z, then its position vector, as shown here, will be equal x in the x direction, y in the y direction, and z in the z direction. And of course, as shown in this figure, the coordinates for the point B is 3, 4, and 5. I explained to you earlier that very often in electromagnetics, we need to calculate the distance from one point to another, because one point we can have the charge, and another point will be the point at which the field is measured or calculated. And we know in electromagnetics that the value of the field decreases as you go away from the charge. So determining the distance and distance vector is very important. So here we have 2 points P and Q. This O here is the origin. So this is really the origin. This is the point 0, 0, and 0. This is the RB is the position vector of point B. So it's pointing from the origin towards B. RQ is the position vector of point Q. Okay. So we want to calculate the vector RPQ. RPQ is a vector pointing from point P to point Q. And if you take a look at this triangle that you have here, you will see that RPQ is equal to RQ minus RB. RPQ, because RQ is the one that closes the triangle. RQ is equal to RB plus RPQ. So this means that RPQ is equal to RQ minus RB. So this is very important to remember when you calculate the distance vector from point B to point Q. You reverse the order, so it becomes RQ minus RB, because otherwise you get a vector pointing in the opposite direction. And again, this is how we do it. This is how it's explained pictorially, but mathematically we subtract the individual components as we do in vector subtraction. So we subtract the x component of Q minus the x component of B, y component of Q minus y component of B, and z component of Q minus z component of B. Example here, we'll take a look at the concept of vector addition. We say that the field due to a charge at a point is E1 equal to 2ax plus 3ay plus 1az volt per meter. This is the electric field resulting from one point in space at another point. And the field pointing, the field resulting from another charge at the same point. So the same point I refer to here is the observation point, is the point at which the field is measured. It's minus 1 in the x direction, 2 in the y direction, and minus 2 in the z direction volt per meter. We want to calculate the total field at this point. Of course, as we explained earlier, when you have the field resulting from two different charges, and these two fields are measured at one point, then the resulting field at that point is the vector sum of these two fields. This is coming from the linearity of the media. This wouldn't apply if we have a nonlinear medium, but this is not the case here. We assume linearity. Linearity means that superposition applies. So the total field must be the sum of both fields. So you can see here this figure illustrates what's happening. You have a charge Q1 at one point in space, giving rise at the point B, at my observation point, so I call it here point B, to an electric field E1, and another charge Q2, which is at a completely different point, giving rise to another electric field E2. And want to calculate the total field. Then the total field at this point B is the sum of the two fields, which is a vector sum of the two fields. So we sum E1 plus E2, and if you do vector summation, remember that the component of the vector E2 is minus 1, 2, and minus 2. This is why you get these minus signs in the x and z directions. So if you sum these two, you obtain the resultant field, or the total field. It has component of 1 in the x direction, component of 5 in the y direction, and the component of minus 1 in the z direction. So it has very strong component in the y direction. It is nearly parallel to the y-axis. And of course, the unit of the resulting field is also volt per meter. We can have here another example. We have 2 points, T and Q. The position vector of point T is 3ex minus 2ay plus az. So it has coordinates 3, minus 2, and 1. And the position vector of point S is 4ax, 6ay plus 2az. So it has coordinates of 4, 6, and 2. We want to define the coordinates of the T and S. This already explained that. We want to determine the distance vector from T to S. So the vector RTS, the vector pointing from T to S. And we want to determine the scalar distance between T and S, not the distance vector, but the scalar distance. So the solution will go as follows. The coordinates are already clear. They are 3, minus 2, and 1, and 4, 6, and 2. If you want to get the distance vector from T to S, this is called RTS. And the RTS, as we explained earlier, you have to reverse the order. It is RS minus RT. You subtract the two position vectors. So it becomes RS minus RT. So it is 4 minus 3 in the x direction, 6 plus 2 in the y direction, and 2 minus 1 in the z direction. If you want to get the distance between points T and S, distance is the magnitude of the distance vector. So once you have determined the vector pointing from T to S, you get its magnitude, and this will be the distance between both points. This diagram will help you understand what's happening. This is the point T shown here to the left. This point S. The vector RTS, the distance vector pointing from T to S, is RTS, and this RT is equal to RS minus RT. And of course, the point here to the bottom is really our origin. So this is the origin here. And I drew T to the left because if you take a look at its coordinates, had negative y. So negative y means if I try to project it here, and I try to see its y component is going to be a negative component. This is why I draw it in this part. If you want to determine the actual distance, it is simply the magnitude of this vector RTS. So once you determine RTS, get its modulus, and this will give you the distance from the point T to point S. So if you take a look at the steps, the coordinates are already given. We know coordinates of T. We know coordinates of S. If you want to determine RTS, it is RS minus RT, as I explained earlier. And if you sum, of course, you have to be careful when dealing with signs, especially when you have negative as in the y component. You get this total vector. This is RTS. You can see RTS is very strong in the y direction, has very strong components, almost parallel to the y axis, because the x and z components are way weaker than the y component. The distance equal to the modulus of RTS, and we agreed that the modulus is simply of any vector is equal to the square of the sum of the squares of the components. So it's equal to 1 squared plus 8 squared with 64 plus 1 squared. So this will give you the square root of 66. It's very close to 8. It becomes actually 8.124. And of course, depending on the units, if these were in centimeters, the coordinates are given in centimeters, this will be centimeters. If the coordinates are given in meters, it will be in meters. Usually, if I don't give you the units, you assume it is in meters. We use the SI units, so this will be meters. So the answer here is 8.124 meters. But I will try to be as clear as possible in the exam and so on, and determine exactly the units. But if not given, you should assume it's given in meters in this case.